So we'll start out and look at some of the significant changes in the 2011 code from previous editions. So if you're familiar with previous editions, this will just help you understand some of the changes, and then we'll be going through some of the design in detail. There has been a significant change to the code format. The code and commentary are now side by side. We have updated to ASCE 710. And probably most of you are familiar that there was a significant change in ASCE 7 from 05 to 10 in the wind load provisions and going to a strength level wind design load. So we had to make some changes in the code to that. One of the real big changes in allowable stress design is that we did remove the 1/3 stress increase. Previous editions of the Masonry Code had allowed 1/3 stress under seismic and wind loads. We were the only material that still had a 1/3 stress increase, and we'll talk about that a little more detail, but we did recalibrate the stresses. We also had a major change in our shear design provisions for allowable stress design. We'll look at that. Just briefly mention a few other things. We will not have time to cover these today, but we did add some deep beam provisions. So beams that are length is less than twice the height that meet deep beam requirements, and there's some special provisions we've added into the code on that. We have modified the lap splice provisions. In particular, there is now the option if you have transverse steel to the lap that you allowed a reduction in your lap splice. That's based on testing that showed that the transverse steel provided confinement. Did that. Quality assurance tables do include code and spec references now, and there's also a new appendix on infills. So here's the format, what it will look like. As I mentioned, the code and commentary will now be side by side, so hopefully that will make it easier for users. As I mentioned, we did remove the 1/3 stress increase option. The reason the origin, the reason for the 1/3 stress was unclear. Some thought it was sort of a time-based loading thing, duration of loading that really does not affect masonry. Some felt it was for load combinations, but it's really a poor way of handling that. So we no longer have the 1/3 stress increase, but as a result of that, we did increase some of the allowables. We did a major a look at all of the allowable stresses. We also then harmonized the allowable stress design and the strength design shear provisions. If we go through allowable stresses just real quickly and some of the changes that were made and were not made. Anchor bolts, there is actually no change to the allowable stress allowable stresses from the 2008 to 2007. There have been a major revision in the 2008 MSJC, and the anchor bolt provisions were harmonized with strength design. In fact, we actually even sort of made a mistake and issued an errata for the 2008 code that allowable stresses for anchor bolt design should not be increased by 1/3 using the 2008 provisions. We increased our allowable bearing stress from 1/4 F'(M) to 1/3 F'(M). We also increased the nominal strength for bearing, and the basis for that change was just looking at other codes. The allowable stress for axial compression is not changed. We didn't feel like we had sort of the data to support that. We did increase the allowable steel reinforcement stress to 32 KSI, up from 24 KSI. That was based on a comparison to strength design, and we also increased the allowable stress, the allowable masonry stress due to combined flexure and axial loads was increased to 0.45 F'(M), which is also based on a comparison to strength design. At first glance here, it may just look like, well, we eliminated the 1/3 stress increase and then increased our stresses to compensate that. But there was some justification for that and a lot of work that we did for that. Let me just briefly explain this graph here. So on the vertical axis, we have sort of a normalized moment, and then on the horizontal axis, we have a reinforcement ratio, rho. A sub S over BD and normalized by Fy over F prime M. So if we look at this for allowable stress design, we have this line here. When the steel stress controls, it's pretty linear. Pretty much if you double the amount of steel, you double the allowable moment. Once the masonry starts controlling though, things change drastically and this line gets pretty flat. Now this upper line up here is, for comparison, is a strength reduction factor of 0.9 times the nominal moment divided by a maximum sort of load factor of 1.6. So trying to compare as much as we can apples and apples here between strength design and allowable stress design. Once the allowable masonry stress starts to control, then allowable stress design becomes much more conservative than strength design. Even if the allowable masonry stress is controlling the design, you're still going to have at ultimate a very ductile failure. That reinforcement will be yielding. So the allowable masonry stress is in a sense sort of just this fictitious thing to control our design, but it doesn't mean that the masonry is actually going to crush at ultimate. So looking at graphs like this and other trial designs is our basis for increasing the allowable stresses. Lap Splice Provisions, 2 changes between 2008 and 2011. We have the same lap splice equation, the development length, same length is used both for splice and development, but we have our equation here when there's this factor K, which is the minimum of the masonry cover, the clear spacing between adjacent splices, and it used to be 5 times the bar diameter, and it is increased now to 9 times the bar diameter based on re-looking at the test results and going through that. So this is a quick table just to show you the impact of that for both 8-inch concrete masonry units, 12-inch concrete masonry units, the splice length required in the 2008 code, and the splice length now required in the 2011 code. So for smaller bars, 3s, 4s, and 5s in that range, the splice length is a bit smaller in the 2011 code, so provides a little more economy in terms of construction and also constructability. Once you get to larger bar sizes, then K starts to be controlled by that masonry cover instead of the 9 dB. The second change that was made in lap splice requirements was the inclusion of transverse reinforcement or confining steel here. So if number 3 bar large is placed transversely within the lap, you have to have a bar within 8 inches of each end of the lap. The transverse bar has to be within 1.5 inches of the lapped bar. You're actually allowed to then reduce the lap length by this factor here. So A sub SC is our area of a transverse bars, a limit on that of 0.35 square inches. So here's a quick example. A number 6 splice, 8-inch CMU, number 3 transverse bars, a reduction factor is 0.481. So splice length gets reduced to 21 inches. However, there is a minimum splice length of 27 inches. So just another quick example. This is for 8-inch CMU bars centered in the wall. The transverse does not really help you with smaller bar sizes. In fact, if you actually go through the calculations, it gives you slightly larger values, the 36 dB. So you just use these values for your splice length. But as you can see, when you get number 6s and above, 7s, 8s, up in that range, if you're having to use these larger bar sizes, then the transverse reinforcement can decrease the amount of splice length that is needed. Quality assurance tables, we now have references to where the various criteria is. That used to be in the IBC. The IBC took it out. Well, I'll just thank everybody. Hopefully this was helpful.